Alright, what's going on, guys? So today we are going to be talking about the metric, and we're going to be talking about it within the context of stereographic projections. Again, if you like this kind of content, make sure to hit that like and subscribe button. Go ahead and go onto my Patreon page, where you will be seeing an increase in the number of, in the amount of exclusive content as well as early content. With that being said, let's get into this video, because this is going to be a long video. So we're talking about the metric today. So this is visual differential geometry. So what we're going to do is we're really going to abuse a lot of visual pictures here. So let's start. Strictly speaking, or generally speaking, the metric is really something that relates distances, when we're talking about stereographic projections, of a sphere onto a complex plane. Here's our sphere, here's our complex plane. The metric is something that relates distances on the sphere to distances on the complex plane. Okay? And so that is what this is right here. So we have some distance on the sphere, anything with a delta, with a hat on it. So delta S hat is this distance right here. And delta S is this distance right here. Okay? And where we want to relate one distance to the other distance. And this here is that metric, is the thing that does that. This tells us the amount we expand at z in the direction gamma. Right? So the amount we expand at z in the direction gamma. Okay, so this distance can bend in either direction, right? It can have directionality to it, and that's what this gamma takes into account. So let's look at this a little bit deeper. So we have, suppose we form a triangle on the sphere, and we want to map that triangle onto a triangle here on the complex plane. Well, by rules of similar triangles, delta S1 hat, right? So that is going to be this little distance right here, and I've blown it up right here so you can see delta S1 hat over R delta theta. So here's R and here's delta theta. This is at R delta theta. So the distance from the center subtended by the difference in the angle. Okay. So this distance here, right? So this distance delta S1 hat corresponds to this distance here. And this distance here is R delta theta. Okay. And that is going to change. That's going to equal, we're going to say that's going to equal R over H, where R is this distance, the height of this, or the radius, say, of the sphere. And here's H, right? So as R increases, you can see that H is also going to increase. So we're going to equate these two things together. Okay? So this is sort of the first premise, if you will, of coming to this conclusion right here. Okay, this conclusion right here is delta S1 hat by R delta H is equal to this. Delta S2 by delta R is going to be equal to this, and we'll see how we form this. So delta S2 hat over epsilon is R over H. Okay, well, again, R over H, R over H. So H again is that hypotenuse. Here's the hypotenuse, delta R. Okay. And here is sort of this epsilon is the equivalent of this big R right here. So I've highlighted in pink these similar triangles. Okay, and that's how we get to this point here. E, or epsilon, delta R, alright, so here's epsilon, delta R is equal to R over H, right? So we have our first premise, our second premise, and our third premise. You might think, well, okay, the second premise, how is the second premise any different from the third one? Well, the second one has delta S2 in it, right? So delta S2 is on the sphere itself. E and delta R, or epsilon and delta R, are not on the sphere itself. So this is an equation that's strictly looks at the complex plane, this equation here relates a distance, or the mapping of delta S square, or delta S2 hat with the triangle that's being mapped on the complex plane here. And keep in mind that this green triangle is perpendicular. You can see a right triangle here, or a right angle, perpendicular to this triangle that we're mapping. Okay, these are the three premises. Now we're just going to work with these, and we're going to develop these two equations. All right, so we already have this one, so that's this down here. When we combine these two guys, right, so epsilon is just this right here. So we multiply both sides by delta R, and we put it into this equation here, and this is what we get. Okay, or we get this, and then from this we do some cancellation and some rearranging, and we get this. So these two equations are going to be useful. These relate the two orthogonal distances on the sphere with big R and H, right? So big R and H are the things that are going to map onto the complex plane, right? So blue is on the sphere, or the hat is on the sphere. Hats are on the sphere, and these two guys are on the complex plane, or are mappings to the complex plane. Okay. All right. So now we take the Pythagorean theorem, right? So according to the Pythagorean theorem, we have this equation right here. So delta S squared, delta S1 squared, delta S2 squared, these are on the sphere. And again, this is just Pythagorean theorem. Squared, 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 so everything's squared. We can now plug we found what these two guys were. We plug them in. And again, we just square everything, and then we take R squared, H squared out, and we get this. Okay. And then again, doing some manipulation, so we replace H squared with this. So why are we doing that? Well, we are doing that because H squared, that's the hypotenuse by Pythagorean theorem, that is just going to be big R squared plus little r squared, right? Because this squared plus this squared is the hypotenuse squared. So that's just another rule of Pythagoras. Okay. So this is just another rule of Pythagoras. This here is just everything in here, and we're replacing that with H also. So we see H being replaced. All right. So now we can say that we come to this conclusion right here, right? So the way we do this is we divide everything by R squared. So everything by R squared, or big R squared, and we get this equation. This should look very familiar to you. This is coordinates for a sphere. This is spherical coordinates, and we came to spherical coordinates by really just considering a stereographic projection of the sphere onto the complex plane. That's something very unique and very interesting that we want to keep in mind. So this is how we calculate distances on a sphere with epsilon greater than 0. The epsilon, again, not being this epsilon. This epsilon is different down here. This epsilon here is the one that we were talking about when we talked about deficit angles in our previous videos. So a sphere, again, is something that has epsilon greater than 0. A hypersphere or a pseudosphere is something that has it less than 0. If we want to project the sphere onto a plane, if the plane were on the opposite end of the sphere, right? So what I mean here is that this plane, right? This plane is it lies tangent to the South Pole. Okay, that's what I meant there. Okay, let's continue. We want to consider this triangle now, because we want to find out what the area of this triangle is. We want to find out what the distance actually of this is and the area. Okay, so this triangle again was the triangle we saw right here. So we're now just considering this triangle. We figured out how we can calculate distances. We can calculate distances on the sphere. Now we want to figure out how we can calculate, or not distances. We figured, yes. So we figured out again. This tells us how we can calculate a distance on the sphere. Okay, we want to figure out now how we can calculate this area on the sphere as well. So let's go ahead and do that. But first, we want to develop another equation for calculating this distance right here. Okay. So we have now delta S squared, or what I have here. So we're now going to zoom into the triangle on the sphere and calculate the area. Okay. And so one way we can do this is first we want to just calculate this. So given this picture, we can develop this equation, and we define A and B to be these two guys right here. So this is sort of a different way of calculating this distance, and the way we're doing this is that this is essentially superimposing a complex plane onto the sphere itself. Okay, and we're asking ourselves, or we're telling ourselves that A is the parameterization when S1 moves in the direction of U, right? So we can imagine on the complex plane, this is the U and this is the V plane, or V axis. So this is on the complex plane, and A tells us how much a distance changes in S1 on the sphere when U changes, and B tells us how much the other perpendicular distance changes when V is affected also, or when V changes as well. So these are essentially parameterizations of distances on the sphere. So when we define these, we can then develop this equation. We really just plug these into here, okay, and we get this. And then we do some manipulating. And when we do that manipulating, we get from here, and this. So this whole thing right here, again, is just this squared, and then this squared is this. And then A squared, U squared, we get all this, right? So I'm not going to dictate all of this, right? Because this is just straightforward mathematical algebraic manipulations. But what we eventually get to, you can pause the video if you want me to go a little bit slower here, but what you eventually get to is this equation right here. And then that gives us this, right? So the distance on the sphere is equal to, if we had some change in our complex plane in one direction and change in our complex plane in the other direction, this should be squared. Right, so G is not squared. Right, so we should erase that like that. And we get this equation here. Now, this is interesting because if F was 0, then that means we are again reduced down to, here I'll zoom in. If this is 0, we're again reduced down to Euclidean distance. So this is kind of interesting, right? Because if this is to say that, so we see that F is the cosine of this angle right here, right? So, and so if the cosine, so the cosine of 90, say if this is 0, right? So if whatever the argument you put into this cosine turns out to be 0, right? So if this ends up to be 90 degrees, you can imagine if the omega is 90 degrees, then the delta S1 and delta S2 are going to be orthogonal to one another, and that means this is going to go to 0. Okay? And we're left with a Euclidean distance. So this is a more general formula of Pythagoras per se. Okay? But applied to curved surfaces. So I'll write that down. General formula of Pythagoras. All right. So now we want to talk about developing an area, a formula for the area on a curved surface. Okay. So the area, so we take a look at this triangle again. Everything's pretty much copied, but now we want to consider the area of a parallelogram that this triangle on the sphere makes. And the way we do that is, here's the base of the parallelogram. Here's the height of the parallelogram. Okay. The height, again, is right given here. Okay. Just by looking at the picture, delta S2 sine of omega, delta S1, okay, so the area again is the base times the height, okay, of the parallelogram. Of the triangle itself, it's going to be 1/2 the base times the height, but we're just looking at the parallelogram. So we get this, and we're looking right here. Okay, so this right here, we're going to stipulate that this is the answer. Okay, we're going to work backwards. So working backwards, if we plug in our formula that we established for A and B, right, so those were right up here, okay, then what we can do is we say, here's our A and B squared, here's our A and B squared, and here's that cosine, right? So F, if you remember, was AB cosine of omega. Okay. We now factor this out, and we get this. Okay. Well, this is the sine squared, and then the square root of all of this is just this, right? Because this is sine squared. So we get this, and then we get this, right? And that matches what we get right here. So this formula right here is the area of a parallelogram. This is the area of a parallelogram on a curved surface. Okay, so this is a more general formula for the area. So general formula for the area of a parallelogram. Because it takes into account curved surfaces. And this all sort of helps us in understanding how complex numbers play a role here. Because again, A and B are parameterizations against parameterizations against the change in some complex plane. Okay. And we can also rewrite this as the determinant. Okay. And this is going to be the square root of the determinant, right? So one way we can write this is you can write it like that also. And that's just a little bit something interesting to keep in mind, that the determinant is something that we can use to calculate the area of a parallelogram on a curved surface. Okay. So we have seen on a sphere, we can calculate the distance as a function of r theta. We can calculate the distance as a function of a and b. And we can calculate the area as a function of a and b, where again, these are parameterizations. This is a distance with respect to how we project onto the complex plane. We can also derive a formula for delta S in terms of delta S itself. The way we do that is from this picture right here. So from this picture, motions are going to be proportional to their distances. So delta S over delta S hat, this should be delta S, right? So delta S hat over delta S is going to be proportional to NZ, so NZ hat, and N little z not hat. Okay, so the distance going from N to Z and distance going from N to the complex plane. Also from this picture, NZ, so again from here to here, over 2R, this distance right here, equals R, so R over NZ. Okay. And so NZ hat, right? So NZ hat over 2R, so this distance, we're forming a triangle, right? So that we form this triangle now. Okay. And R over NZ, so R over NZ is forming this triangle right here. Therefore, little r right here is equal to delta, or the little r here is going to be delta S prime over S. Okay, so that's going to be a distance on the sphere, with the distance in the complex plane, which is distance in NZ. Right, so NZ prime over NZ, okay, which is again this distance here. Right, so we found that NZ hat is equal to this right here multiplied by 2R, so we get this. Again, this is just algebraic manipulation, and then we get this equation right here. And if r, little r, is equal to z, the value of z, because again r is this distance right here, so the absolute value of z is just going to be the numerical value of that distance. And nz squared, right, so this right here, this distance is going to be this squared plus this squared by Pythagoras, this right here. Then delta S over S, okay, is going to be this right here, right? Because we said we had this and we had this. Okay, we're combining them to get this, and eventually we get a formula that relates the delta S on the sphere, again with this should be delta S on the plane. So a stereographic projection of our a stereographic projection of our sphere on the complex plane will give us a formula that relates delta, the new metric with the old metric, right? So we can also derive the formula for the magnitude of the point on the plane in terms of theta, right? So this angle here, right? So that angle there is this angle right here, okay? And what I'll do is, just for sake of having the picture with us, is I'll take this guy, I'll copy it, and I'll paste it down here also, so that we're not, and then I'll move it, shrink it up, and I'll move it, just so we have this picture with us. So the point here, again, is we want to say that sine of theta over 2 is equal to 1 over n minus z. And we can look at this picture. So n minus z, so that distance right here, okay, and sine of the sine right here, right? So here, sine of this guy, again, sine is this divided by, here, I'll write this out. If you remember from trig, sine of some angle is equal to opposite over the hypotenuse. Right, so the opposite, if we're taking r to be 1, here's our r, and here's our hypotenuse, right? N and z, and that distance. Okay, cosine is going to be this, right? Because here is our n minus z, and the cosine is going to be that distance, that z distance, divided by the hypotenuse. Okay? So when we take these two formulas into account, we can combine them into a cotangent, like this. And then we fill everything in, and we get this equation here, right here, that tells us how we can find the distance of z in terms of the angle that's subtended when we draw that, when we make that mapping. Okay. So these are all interesting and unique ways or relationships that define what a stereographic projection is. We want to get a little bit more into this, right? So the idea here is that we're going to develop stereographic formulas that now relate points on the complex plane, okay, but with a new point in mind. This new point in mind is going to be z prime, okay, and z prime is going to be important in helping us understand that stereographic projections are going to be things that preserve circles during that mapping, when we map distance, when we map things from here, from the sphere to the plane. So now we are actually going to talk about stereographic formulas and how these stereographic formulas relate 2 points to each other on the complex plane, right? And so these 2 points are going to be linked to each other by means of the stereographic projection. And so the way we're going to do this is by considering the following picture. We have 2 points now. One is z prime, the other one is z, and we want to see or show a couple of relationships here. So the first one is going to be this relationship right here, that z, our distance, is going to be equal to the height of the plane, the complex plane, to the sphere, to the surface of the sphere. And we're going to see how we're going to do that. So first off, we are going to look at this relationship here. This relationship is just to say that as we increase the point z on the plane, we also increase the distance of, or we're also actually proportionally changing the distance of z prime as well, right? So z, so I was looking at z hat, but as we increase z, then the value of z prime should also increase. And what we want to do here, so that's this first ingredient. The second ingredient is going to be this right here, which is z over z prime, right? So z over z prime is by similar triangles, right? So we're considering the big triangle here and then the small triangle here. So this is 1 minus z, this distance from n to this point right here. And that's where we get this right here. So 1 is to z as 1 minus z is to z prime. So those proportionally change to each other as well. And what we also want to show is that from Pythagoras, z prime plus z, right, so the distance here, z prime to z, right, which is this distance, is equal to 1 squared because this is the radius, which is 1. Okay? And so when we say this, then we could rearrange a few things and we get this. Okay? So since we said this, we can plug a few things in. And when we plug them in, we get to this point right here. So this is to say that the value of z on the plane, the complex plane, is that squared is equal to this relationship right here. So 1 plus big Z, 1 minus big Z. Okay, this is a stereographic formula that relates the height, the distance here from the plane to the sphere to the actual value of Z itself, which is quite interesting to actually think about and ponder. The next thing we want to do is we want to say, okay, well, what's 1 plus Z squared? Right, so that's going to be 1 plus this. And when we do that, we get to a relationship that looks like this. We get 1 plus Z squared equals 2 times Z over Z prime. Okay. Well, okay, so we added 1 plus Z squared. Now let's put 2Z on top of that. Right? So we're going to put 2Z on top of this. Okay? So here's 2Z on top of this, and we get this right here. So in the end, Z prime is equal to this. Right? So the coordinates of Z prime of this point right here can be fully in terms of the coordinates of Z, which is what we're showing right here. Because without the absolute value bars right here, this is actually a vector in our... When we put the absolute value bars, we're looking at the magnitude of that vector in the complex plane. But when there's no vector value, or when there's no magnitude being expressed, then what we're actually getting are the components. And this is how we write that out. Okay. So now we're getting coordinates of Z prime in terms of Z, and we can get the distance above the Z above the C axis, or above the C plane, the complex plane, in terms of Z as well. So that should tell us everything about how we relate this second point to this original point. We can also show this, and the way we do show this relationship is through this step, because we found that this is equal to each other, and so if we plug this in to this formula, we effectively cancel a bunch of things out, and we arrive at this point, which is that Z squared is equal to Z squared. Okay, so now we want to see how circles are stereographically preserved. We want to show that a circle in C is preserved on the sphere. A circle on the sphere stereographically projects to a curve in C, whose equation looks like this. Okay? Because if we start with this equation and we rearrange a few things, we just multiply a few things out. We're multiplying things out. And then we get to this, and I won't go through the details. You can pause the video if you want, but we ultimately get to a point where we're here, and then we have this relationship right here. And by means of completing the square methods, right, so the completing the square method looks like this. If y equals x squared plus bx plus c, then we get this, right? So this is something that you typically learn in some algebra class or maybe calculus class. We can find that b, in this case here, that b is equal to these two values for each one of these dimensions, right? So this is in the x dimension, y dimension. Okay. And then So we add that B in, right? So that's this right here. So there was no C, right? Because there's no constant being added to these. So we add that into here like this. We subtract both from this side of the equation to get this, and we multiply this guy by k minus n, right? So k minus n over k minus n. So we get similar denominators across the board. So we can combine them all in one go, like this. And then we can cancel these two guys out when we multiply this out. And we end up with the circle. This is a circle, so effectively what this means is that this equation is a circle when everything is multiplied out. So this here is a circle in the plane, right? Because x and y are coordinates in that plane of z right here, x and y. Okay? And the circle has a center of this and a radius of this. Right? So this side tells us what the radius is. This side tells us what the center is. Okay. So now we come to here are the coordinates in C. This line here can give us the coordinates of the circle. Okay, this or it's not a line, right? This equation tells us everything we need to know about the circle in the complex plane. When k is equal to n, it reduces to a line. Okay, so given, and you can see that because when k equals n, effectively what we get is a cancellation of the x squares and the y squares. So we have no more square components to the x and y, so we're left with x plus lx plus my, and we can reduce that down to a line. Okay, and that line can give us, it tells us something about this line here. And so given that we have a line that maps to a circle, well, that means every point on the circle has a line mapping to it, given some point z prime on the sphere. So if the line maps to a circle, then circles on the sphere will map to circles on the complex plane as well. Right, so this was sort of a grand tour of stereographic projections. This grand tour, again, just to reiterate, we've seen that we were able to show that circles map onto circles during stereographic projections. We were also able to show relationships between distances above the complex plane and the points on the complex plane that are stereographically projected. We were also able to see, show that metrics are related to each other, and this is how the metric is related to each other on the sphere and on the complex plane. And we were also able to derive some general formulas for Pythagoras, and or general formulas for distances on the sphere and for areas on the sphere. And we were also able to show how the metric can be written in terms of how far you are from the sphere and the angle you've subtended from the sphere as well. So this was a grand tour of the metric in the context of stereographic projections. Again, if you like this kind of content, make sure to hit that like and subscribe button. Go onto my Patreon page where you will be able to find exclusive content as well.